Good morning, everyone. Thank you for taking time out to attend today's webinar on developments in mass timber, a Canadian perspective. My name is Nirmala Thomas, and I'm the Director Market Development at FII India. Today's webinar duration will be of 1 hour and 10 minutes approximately. FII India is also known as Canadian Wood, the crown agency of the Government of British Columbia in Canada. We are a non-profit organization with a mandate to educate and promote use of BC forest products in the offshore markets of the world. British Columbia is recognized as a global leader in sustainable forest management. Canadian Wood has been actively promoting building with wood in India through 5 legally sourced species from BC, namely spruce pine fir, what you call as SPF, Western hemlock, Douglas fir, yellow cedar, and Western red cedar. It is a known fact that in 2017, Canada boasted the tallest mass timber building in the world. Vancouver's 18-story Brock Commons tall wood house residence building was completed in 2017 using engineered mass timber. Since 2017, mass timber building construction has taken off across Canada. The Model National Building Code, what we call as MNBC of Canada, allows for 12-story mass timber buildings to be constructed. You'll get to hear more of this from our speaker today. Timber buildings are grabbing headlines around the world. There has been increasing talk of a renaissance in timber construction. Advancements in wood product technology systems are driving the momentum for innovative buildings in Canada. There are nearly over 500 mass timber mid-rise buildings across Canada, which are either completed or at various stages of development. This is as per information available at Natural Resources Canada. Canada's forest and lumber industry is one of the largest in the world. The government's support for wood construction materials has helped encourage investments in this market to find innovative products to use. Without taking much of your time, I would like to now hand it over to Peter Bradfield, Technical Advisor FII, to formally introduce our guest speaker for the day, Derek Newby, to all the guests attending. Over to you, Peter.
Thanks, Nirmala. And good morning to everyone. It's my real pleasure to welcome you to today's webinar and to introduce our presenter, Derek Newby. Derek's a vocal advocate for the widespread adoption of mass timber construction and the application of passive house principles in buildings. Derek Newby is principal at Diamond Schmidt Architects in Vancouver, BC, member of the Architectural Institute of British Columbia, member of the Royal Architectural Institute of Canada, a lead accredited professional and a certified passive house designer. Derek undertakes work for private and public sector clients and has been called on to advise local and provincial governments on timber architecture, thereby influencing policy while increasing awareness. Excuse me. He has served as a member of advisory design panels for the cities of New Westminster and Surrey, and has made a major contribution to many infrastructure projects in the city of Burnaby throughout his career. His portfolio of work includes mixed use, office, housing, and academic facilities, many of which prominently feature mass timber. His achievements include timber projects such as the all timber, prefabricated, modular Dilly Creek Workforce Accommodation Facility, Orchard Commons at the University of British Columbia, featuring 2 student housing towers connected by a timber-framed link, Solo, a prefabricated, all-timber, off-grid, net zero energy passive home on a remote site near Whistler, BC. Lead design for a 7-story mass timber passive house apartment building in West Vancouver. And lead design of the 38-story timber hybrid Canada's Earth Tower in Vancouver, which is proposed to be among the tallest in the world. It's rather an impressive list. I'm sure it's not exhaustive, but just gives you a taste of the kind of work that Derek's been heading up. Derek's clearly passionate about his work and has delivered many public and private presentations on timber buildings. So this is just one of those presentations, the latest. So without further ado, I'm going to hand over to Derek. Before I do so, I would ask that you, the audience, submit any questions you might have during the presentation in writing via the Q&A tab, and I will collate and present as many as we can at the end of Derek's presentation. So thank you, and over to you, Derek.
Thank you very much, Peter. Can you see my screen? You can. As Peter, great, thank you, Peter. As Peter said, my name is Derek Newby, and I'm an architect and principal in the Vancouver studio of Diamond Schmidt Architects. We're a pan-Canadian practice based in Toronto to begin with, but with offices in Vancouver and New York City now. And I'm really delighted to be able to take this chance to speak to colleagues in India to share our experience with mass timber in our country. The agenda for today is quite high level because we have an hour, and we could easily talk for a week about mass timber as it applies to our industry. I want to start with a very simple and profound statement, and that is that timber is the only construction material that we have as architects that's grown by the sun. This is a simple sentiment, something that's beautiful. It speaks to the miracle of photosynthesis and the fact that things that we grow on Earth are closer to the harmony that we need to find with the planet. So, you know, the fossil fuels that we've been using for decades is really stored photosynthesis that has been put into the earth. We're talking about moving into a future where maybe we leave that fossil fuel in the ground and we start using more natural processes. The big takeaway that I want to leave you with is that if we don't grow things in the context of architecture and construction, we have to mine it. And I would say that the consequences of most mining operations are far more significant than a sustainably managed forest. So, you know, timber is often critiqued for the logging practices that can be harmful to ecosystems. I'd remind you that most mines start with a clear cut to begin with to remove overburden before we can get to the mineral resources that are beneath. But I can tell you that forests today in the North American context, and particularly British Columbia, have really advanced their management practices to the point where we don't have deforestation in British Columbia anymore. There's no net deforestation. And the forests are managed in a very sustainable way to minimize negative influence to habitat. So it's a much different forest industry today than it has been in the past, and that's cause for optimism. To start with, the key reason why I'll advocate for the use of timber in architecture is really the greenhouse gas emissions problem that we all face on Earth. Buildings account for about 40% of the resources that we make worldwide, and they account for something like a third of the emissions. These are UN sources. You know, the bottom line is that buildings are too important and too big to ignore. And as architects and people in the construction industry, we really need to lead and to reconsider the choices we're making in how we're going to make buildings and the materials we're going to use. And why is that? Because our Earth is approaching 8 billion people. For a country like Canada, which is diverse and big in geography, you know, we only have 35 or so million people. The present rate of growth in the world is about 2 Canadas a year, which is shocking to a Canadian to realize. But with that growth on Earth, there comes an amazing demand for new construction, for housing, for buildings to replenish the stock. So to accomplish that, we really can't ignore the emissions that go into buildings, both in their creation and in their operation. It's simply too big to ignore. We have a role to play in the greenhouse gas emissions problem that we face. So the imperative we're left with is that we have to use less energy to make and operate buildings. And there's ways to do that, just waiting on the shelf for us to apply. There are choices that we can make. And the reason is that energy use generally means emissions. We're fortunate in British Columbia that most of our electricity comes from hydroelectricity, which is relatively low emissions source of energy, but still has consequences. Not all of the world is so fortunate. We still see a lot of fossil fuels being used to make electricity and fuel for our buildings. And if we simply make buildings use less, we'll be doing our part to curb climate change. Presently, the codes that we operate under in North America and Europe, I think, maybe much of the world, are focused primarily on the commitments around operating emissions. So by this, I mean the energy used to run a building after it's been built. So increasingly stringent requirements so that our buildings are on a target or a path to achieve net zero by 2030. It's an ambitious goal, but one that's hopefully achievable with many building types. At the same time, as our operational emissions become under control through the regulations that we have to operate under, the significance of the embodied emissions, those emissions that are expended as a result of making the products and materials that create the building, this becomes very obvious. So we start using less to operate, the energy that goes in to build becomes a real issue. So where to intervene when it comes to embodied emissions? We know that the structure of a building accounts for about half of the emissions in the building, give or take. So it's a sensible place to start. So can we start building structures for our buildings that are less harmful or less greenhouse gas intensive? So what I'll say is that, timber is a big part of that solution. And on the operating energy side, passive house principles are a big part of the solution. So these are two technologies, one that addresses embodied emissions in timber, the other that addresses operating emissions in passive house principles. And if you put them together, you have a perfect marriage of state-of-the-shelf technology, so things we know how to do well today, that can be applied to solve some of the greenhouse gas emission problems that we have. If you haven't heard about passive house principles, I can tell you that it's a low energy building standard that works in any climate zone. So from the south of India to the Himalayas, in desert climates, in cold climates, the principle is to make an incredibly robust building envelope so that very little energy is required to make the conditions inside comfortable. And that combination, I would argue, is the best that we can do today. So I would love nothing more than to see more buildings being made out of timber and more buildings being made to the passive house standard. So the emissions imperative is really what's driving many of the advancements in timber construction, but I think I'll just take a moment to go through some of the benefits we see in British Columbia as a practitioner to using timber in architecture. So first, wood stores carbon. That's the simple message. And buildings being things that last for a very long time, hopefully, it creates a way of sequestering that carbon indefinitely. So the carbon from trees, are part of the terrestrial biosphere. So the carbon exchange that happens in a cycle between the atmosphere and the first few meters of soil, that is emissions and a cycle of carbon that we can manage and doesn't really cause the global warming that's the problem. When we take fossil fuels out of the ground, we add it to the terrestrial biosphere, it creates an imbalance, and that's what's leading to climate change and global warming. So Canadian softwood lumber, so coniferous trees that are harvested from the west coast of British Columbia mostly, are about 50% carbon by weight. So we know that every kilogram of wood that we put into a building is a half a kilogram stored of carbon emissions. So we also know that timber buildings tend to just have fewer emissions beyond the materials themselves compared to other types of buildings. Some studies have indicated that greenhouse gas emissions are reduced by as much as 70% over conventional concrete buildings. And that's really a result of the material characteristics of timber. So timber, to make the equivalent space, tends to be lighter weight, tends to require less processing, so therefore less energy required to make something useful. So the strength of timber as a material largely is measured in its ability to do things more effectively from an emissions point of view. Next, this whole notion of a shift toward a renewable industry. What we're really talking about here is the shift in our industry from simply being depletion to being a more circular future where we start giving back as opposed to simply consuming products and materials. And we're just at the start of that right now, where we truly can have sustainable buildings. There's much to do, but using wood is a big part of this pursuit. Of course, this does rely on sustainably managed forests. If we're doing clear cuts and not reforesting, that's completely negative. It's not something that would help this shift toward a more circular future. We need to make sure that we follow up through the cycle from sapling to cut wood that goes into a building. It needs to be seen as one thing. We also know that from our experience that timber buildings tend to go up faster than concrete or steel buildings. And a big part of that is that you're reducing wet trades. We don't have the typical concrete cycle that requires forms to be made, concrete to be cast, days to elapse so that strength is achieved before the forms can be stripped. So there's a cycle of time that comes with concrete buildings, particularly multi-story concrete buildings, that is simply slower than a timber building where timber is installed and it's at its service strength immediately. So there's no lag. The timber building can be in service immediately. We also know that processing timber is a much simpler thing. It can hand tools, relatively simple technology can be used, although increasingly automation is really defining how timber is processed. An important consideration is that timber buildings tend to be have less weight than concrete or steel counterparts, and this is important because when we have less weight, our lateral forces become smaller, our dead load forces become smaller, so it means we can have smaller footings, we can have less shear elements or reduced in size when we're in seismic zones. And the material characteristics of wood are, it's just simply lighter to get a similar strength compared to other things. So, timber weighs about 35 pounds per cubic foot. Concrete would be about 130 pounds per cubic foot. So there's a dramatic reduction in weight in these buildings. Another factor that's often considered, particularly in urban settings, is that timber buildings are just less noisy to build. There's none of the chipping, concrete cutting, coring, grinding, all of these very noise-intensive processes that come with concrete buildings. You tend to avoid much of that when the structure is based in timber. One of the biggest questions that we always face is that's great, timber sounds wonderful, how much does it cost? And it's an emerging science. I would love to know how much timber buildings cost in a consistent way as well. What we're seeing is that there's a small premium typically for timber buildings right now in the markets that I operate in. But under the ideal circumstances where a building's purpose designed with timber in mind, it can be cost neutral or potentially even cheaper than alternatives. It really varies greatly according to skill, the availability of trades and expertise. So it's an emerging field. As we see more timber buildings coming online, I think we'll see the costs becoming even more competitive. I think that's just the market at play, and we can count on that. So we're talking about timber today, and to talk about mass timber, there's a little bit of vocabulary that we really should cover, because there's lots of different kinds of mass timber and they all have unique characteristics. I would start by distinguishing that what I'm talking about today is engineered mass timber. I'm not talking about light wood frame buildings that are made out of small dimensional lumber and built into frames and platforms. That's typically used for house building or small apartments. I'm not talking about heavy timber, which are sawn timbers out of big logs. Large timber members in a post and beam configuration are built. I'm not talking about that. What I'm talking about is engineered mass timber. So engineered mass timber is a combination of composite wood elements that are either columns, beams, or even floor slabs. And these are sophisticated new products that have been engineered to perform even better than natural fiber that you would see in a heavy timber building or a light wood frame building. So forgive me for all these letters on your screen, but it seems like our industry likes to use abbreviations to describe the different kinds of wood that we use. So there's really three sources of wood that come and turn into these mass timber products. So there's dimensional lumber that gets glued together. There's veneers, like veneers that you would use in plywood that get glued together. Or there's small pieces of wood, often from relatively minor species or waste wood that get glued together to create elements. So very quickly, glue-laminated timber, or GLT, are typically used for beams and columns, but can be used as floor decks or roof decks as well. They're dimensional lumber glued up as much as 2 meters in height, sometimes as much as 300 millimeters in width or wider, different sizes for different span conditions and different load conditions. There's CLT, which is cross-laminated timber, which takes that same dimensional lumber, 1x6s, 2x6s, 1x4s, 2x4s, and glues them together at right angles to each other in an odd number of lamella that then is glued together and creates a billet that can span 2 directions and can be later machined for walls, roofs, or floors. MPP is mass plywood panel. Mass plywood panel is really plywood that gets very big so that instead of being used as a sheathing material or something you use in cabinets, they become massive elements that can form floors and span distances, or could be used as walls or roofs as well. NLT and DLT are nail laminated timber and dowel laminated timber. So again, these are dimensional lumber placed on edge. And in the case of NLT, they're nailed together with steel nails to create one mass element that can span well in one direction. DLT is similar to NLT, except we remove the nails and we use hardwood dowels to connect all those wood members together. So it can be an all-wood adhesive-free panel, which is attractive in some cases. LVL is similar to a mass plywood panel, where it's really just wood veneers that are configured differently and glued together to make smaller elements that can span further. The last two, LSL and PSL, are really small pieces of wood, sort of like the size of a ruler or a meter stick, that are then glued together. So it allows you to use what is a byproduct or waste material often and make very strong, high-performing wooden members with the use of glue. So a lot of names, but it's really all the same thing. It's softwood lumber with know-how, smarts, and glue to turn into something that performs better than conventionally sawn dimensional lumber. The fabrication of mass timber buildings is highly automated now. We've seen a lot of innovation in this industry start in Austria, Germany, Switzerland, where a highly mechanized workforce is expected. So a lot of the tooling comes from there. We're talking about multi-axis CNC mills. You can see in the top picture. or different kinds of presses that can be used to make these products that you've seen. What this allows is for a lot of processing to happen in the factory. So panels are cut to size, they're routed for services, they're pre-drilled for connections. A lot of that processing is done in a digital fabrication technique these days. Of course, when we talk about mass timber elements, we need to think about how they join together, because by themselves, they don't really get buildings done. So the connections are fundamentally important. Most post and beam buildings, you see basic connections like on the screen, which are steel fabrications made out of plate steel. They often have through bolts, and they're very simple. They've been used for over 100 years now. Because they're exposed in many kinds of buildings, they require fireproofing, so an intumescent coating or gypsum board laminated over top. And they're a bit coarse and clunky, and don't generally do well with shear. Modern connections, however, are quite different. They're far more sophisticated. There's been amazing innovations happen in connection technology right now. So what you see are often concealed connections that are routed into the wood members, fastened by sophisticated wood screws. The advances in wood screw technology would be surprising if you're a follower of fastener technology. There are many, many different kinds of fasteners that do different jobs. We can see screws as long as 1.5 meters for some applications, or some that have different characteristics depending on the application that they are applied to. Here's an example of one of those connectors I'm talking about, which is a aluminum member that allows 5 screws of different lengths to be configured to allow 2 panels to be connected at a right angle. So this is like toe nailing that you'd see in normal wooden construction, but a much more sophisticated, much more heavy load capacity in these connections, just through clever engineering. Another example, these are glue-laminated timber posts that will, in service, connect to a beam. That beam will have the opposite connector to slip in over top of the connections that you see here, and you'd never see them. They're designed so that under load, they become tighter and stronger. This is what the other side of that joint would look like. So it's a complementary fit between the 2 sides of the joint, using screw technology again, depending on the type of wood employed. Some examples of some of those fasteners I'm talking about. The top screw is your conventional wood screw that you would find at any home center. The screws below are customized with varying depths of threads and various conditions to do different roles when we start putting wood together. So an example of a beam that's prefabricated in a factory waiting for connections in the field. So you see they do as much work as they can in the shop, so that when they're in the field, it's more a matter of erecting the elements as opposed to fabricating them. Fabrication takes place in the shop. I should say that there's a lot of innovation happening with timber hybrids. So timber buildings that use steel or timber buildings that use concrete. What you see on the screen here are some examples of concrete timber hybrids, where we use a composite action between a concrete topping on top of a timber floor. This allows better acoustics, often creates a very durable floor if you're in a lab condition or other high demand area. Of course, with that mass that comes with the concrete topping, we can have improved vibration control. And some of these connections allow for the wood to have improved performance as a diaphragm to resist lateral forces. So as much as we talk about timber taking the place of concrete or steel, there still are applications where we reduce the amount of concrete in the building, but still use it strategically to advance some of our overall goals. One thing that people need to understand is that in a contemporary sense, mass timber buildings are prefabricated buildings, and they generally are modular as well. And why do I say that? Well, The kind of work that you need to do to handle mass timber elements generally requires some hoisting material, the ability to handle big, relatively heavy pieces. So that tends to happen in shops. So this is a roof panel for a project of ours that's being fabricated in a shop. You'll notice that it's modular in so much as it's made so that it can go down the road to the construction site. So they're about the size of a trailer that can be hauled down the highway. What we can do in the factory is pretty remarkable. We can put together all the structural elements. We can install insulation. We can put membranes in. We can pre-plumb these panels with sprinklers. There's much that can be done in the factory, which means the workflow on site is more an issue of erecting pre-made elements as opposed to fabricating them in the field. And we know that that just makes a more considerate workplace for all the people building this. Who wants to be standing in the rain or the snow with a handsaw trying to fabricate wood outside when you can work in a facility like this? This is a project that shows how panelized flat pack mass timber elements can be prefabricated in a factory. And in this case, this is waiting to be loaded into the shipping container that's on the truck behind. You'll notice that hoisting points are built into these panels so that they're prepared to be hoisted off of out of the container as soon as they're delivered, and they're often planned so that they come off in the order that they get erected. So a lot of automation and planning goes into the prefabrication that happens. This is an example of a prefabricated modular roof element, this case an expressive curving roof element, that again was limited by the size of the load that could go down the highway, but as much work as possible took place in the factory so that a crane was required with a relatively small crew to install in the field. This is an example of a prefabricated wall that's a passive house standard wall. It's laying flat because it's a passive house assembly in a very demanding climate in the mountains. It has about 60 centimeters of mineral wool insulation as part of it. So that's why you see the exceptional depth to this wall. But the fabrication techniques that happen really are enabled by the factories like the one that you see. In fact, this is a mass timber factory that mass timber elements are being built in. And those panels, again, truck-sized panels, show up on site with a very small crew and can be hoisted into place and connected quite effectively. So I know many people will be thinking of issues and misconceptions around timber, and there are many. And each one of these issues that I have on my screen could be a webinar of its own. So there are issues around fire safety that we need to address. There's issues around durability, around acoustics, moisture, mold, insects, seismic performance. All of these things are on people's mind when it comes to timber. I'm going to focus on fire safety today. And it's not because the others are unimportant. It's really because each one of them could be a webinar. I can tell you that the other issues have been fully addressed and don't present a barrier to the use of timber in almost every application. So fire safety is the one that we really need to prioritize when we think about timber buildings. So as I was saying, fire safety is our first priority as architects. We have a duty of care to the public that use our buildings, and we must provide safe service for the people that use them. In the North American context, and particularly in Canada, there's a multifaceted approach to fire safety in buildings. So it's not one thing, it's many things that allow for fire safety to happen in buildings. We should note that our building codes in North America are really about the preservation of life and safety in buildings. There's no requirement for buildings to be fireproof or earthquake-proof. They need to be resistant to fire conditions and resistant to earthquakes. So what we need to do is make sure that we design a building that's safe for people to live in, but also safe to exit should something happen. One thing that I will advise is that during construction, timber buildings are particularly vulnerable to fire safety. And that's because all of these multifaceted approaches aren't in place yet. They're not together as a system. So during construction, builders need to be very careful to make sure that the fire safety is accounted for. So when I say multifaceted, you know, I think there's 17 different elements here, and there's probably one more. There's a number of things that we do to make timber buildings safe. And as buildings become more risky, so the taller they get, the more things come into play. So it's not one factor, it's many. So we limit the combustibility of materials. We compartmentalize the floor plan so that smaller compartments contain fire should they happen. We limit the size of buildings. We limit the area that they can cover. We make sure that incompatible occupancy types don't happen in the same building. We make sure that access to exits is supreme. We make sure that those exits are redundant and smoke proof and fire resistant. We also sprinkler our buildings in North America. This is one of the greatest innovations I think that we've had in building safety is providing fire sprinklers throughout buildings. It's automatic now in these kinds of buildings. Sometimes we'll even put an additional on-site water supply in order to make sure that in the event of a disaster, you know, if the fire department can rely on water on-site to fight fire should it happen. So the last thing that the timber advocates will tell you about is that timber itself has limited combustibility. And what I mean by that is big wood elements tend to burn at a very predictable rate. And they tend to self-extinguish or to burn very slowly after a char layer is developed on the wood. So just like anyone who's stood beside a fire before, you know that you start fires with small kindling, small sticks. You don't start with a big log. The big log will smolder and have a hard time getting going. So what we want to do is make sure that we oversize exposed timber elements, so those elements that are exposed to a fire condition, so that they can build their own char level in that eventuality of a terrible fire, and provide that time that we require for people to exit safely and the time necessary for a fire department to respond and put out the fire. So what we have right now is sort of a perfect combination of factors that are making some exciting developments. So we have the advancements in engineered wood, so the kinds of mass timber elements we've been talking about, you know, much higher performing than conventional wood, more stable, easier to work with, longer spans, better conditions, higher strength. We have advanced processing technology, so the CNC mills that allow us to machine wood to very high precision, very effectively. We have advances in the connection technology, so very sophisticated connections that make putting buildings together faster, easier, stronger. We have building code revisions that allow for the use of more timber in construction, which is enabling much of the innovation that we're seeing. And last, we have global commitments to greenhouse gas emissions, which makes timber a natural choice. So together, these really mean a renaissance in timber construction. And we're seeing it happen in North America and in Europe. And it's going to, I think, take off elsewhere. We're seeing it in Australia. So I know I've used about 30 minutes of time, but I will run through a few projects quickly, just to show you some conditions in British Columbia and Canada where mass timber has been applied. So this is an interesting project from my office. It's actually an addition. So the lower two floors were an existing building, and they wanted to expand it. The only way to expand it effectively was to put a timber structure on top. And that's because the foundations of the existing building couldn't take something heavier. So the innovation of timber being lighter and more effective let us find the solution that gave more life to this building. And we created some amazing spaces inside. Curving wood elements is really not a barrier. It's something that fabricators can do quite readily. This is one of those panels that made the roof that I showed you in the previous building. This is what they look like before they were in service. Other more conventional examples, this is a sort of a hybrid building. So it's a concrete building with wood elements. So you see glue-lam columns and beams resting on steel connections with a wooden deck. Sometimes, you know, we get very creative with how the wood elements can be deployed. So this is the National Arts Center in our nation's capital in Ottawa. This is a Douglas fir glue laminated coffer ceiling that's made out of modular elements that are repeated. And the curtain wall, the glass wall on the left-hand side of the screen, is also supported by a wooden wind structure. Sometimes we can use wood to evoke connections to culture. In this case, this is a building at Thompson Rivers University in the interior of British Columbia. This recalls an Indigenous pit house that was part of the original population who lived in the area. So we have a glue laminated structure, but logs, actually just peeled logs where the bark is taken off, and using them to span between the glue lam elements. The logs that are used in this building were actually killed by beetles in an epidemic that happened in the British Columbia forest, where pine beetles killed a lot of trees, and the wood was standing waiting to be used. So we harvested it and put it into use, locking up its carbon for the life of the building. We have, expressive large buildings. This is an institutional building at a college just outside of Ottawa, with sweeping glue lam arches that support a roof. Or part of that building contains, factory space, shop space, where we've taken out steel trusses that you would normally see here, and we've replaced them with glue lam beams. The reason why is that it was more cost effective in this case. A fabricated truss was more labor intensive to make than glue lam beams that could then support steel purlins and steel deck. The building that Nirmala spoke about at the beginning of the presentation is Brock Commons Tall Wood House. This is done by Acton Austri architects, colleagues here in Vancouver, and engineered by Fastenep, also local engineers. So this is a 52-meter tall concrete hybrid building with concrete cores and a repetitive pattern of glue laminated columns and CLT decking, with also a very innovative cladding system that was able to be installed as the building goes up. There's more aspirational projects on the boards as well in Vancouver. This is Canada's Earth Tower by Perkins & Will Architects in Vancouver. I was involved with this project. It's proposed to be a 38-story mass timber hybrid building with concrete cores and timber principal structure. The idea of expressing timber structure inside to the greatest extent possible to show the warmth of the wood. A very important building in the life of mass timber buildings in Canada was the Wood Innovation and Design Center by Michael Green Architecture. This was an important building, one of the tallest buildings of its kind when it was built, but again, a mass timber building built in Prince George, British Columbia. This is the house that Peter was describing in his introduction to me. This is a purely wood off-grid house that is really a temple to Douglas fir. So what you see here is glue laminated columns, dowel laminated timber walls, and CLT floors, creating a warm embrace of wood that isn't able to be achieved with any other material. So those are just a handful of projects. There's many, many more. And there truly is a renaissance in wood happening in North America, in Europe, in Australia. I think it will take off around the world. We just need to advocate for it and understand the benefits. If you want to look at more projects, if you go to www.naturallywood.com, you will see a number of case studies that show the possibilities with mass timber construction. So with that, I will turn it back to Nirmala.
Thank you, Derek. That was a wonderful presentation. I'll now hand it over to Peter to begin the Q&A session. Peter, please go ahead here.
Yes, thanks, Derek. Well, I'm sure you'll all agree that was a very informative and entertaining look at mass timber construction. Thank you very much, Derek. Some great examples of projects and images, and a lot of food for thought for the for Indian architects. I'm sure we see a lot of inquiry. So this was, one way of bringing together all of the inquiries that we see in India around mass timber. We did receive a number of questions throughout the presentation. There are a couple of key questions that always come up, and so I can summarise these as fire issues. You know, fire, how the mass timber buildings perform in fire. Of course, you addressed that. So I think you pretty much covered everything there in terms of fire. In terms of durability, there's questions around, you know, the Indian climate being humid and hot, and a whole range of microclimates across the country. How will these buildings perform durability-wise? So I think maybe that's the first question we could cover.
Right. You know, I think those questions around long-term durability of timber are completely reasonable. We face the same issues, maybe for different reasons, in the climate zone that we work in. But wood is a natural material. It is sensitive to the climate conditions that it sits in. However, we know that if we keep wood inside the enclosure, it can have an incredibly long service life. So what we really need to be cautious of is repeated wetting of wood. We would also note that engineered wood products behave differently than sawn lumber or sawn timbers, right? They're much more stable dimensionally. The use of the adhesives that are required to make them work together makes them just behave better. So I think it comes down to considerate detail, making sure that wood doesn't come in contact with the earth, making sure that there's you know, separation between any moisture hazard in particular. But we use timber in very demanding conditions, places like hockey arenas, industrial facilities. It can stand up to very harsh conditions. It's really just a matter of detailing correctly.
Yes, I couldn't agree more. And I think important point, whether we're talking about fire, or we're talking about durability, or even termites in India, you know, we're not saying that any of these products are fireproof or termite proof or durability proof. What it comes back to is good design, in my opinion. And we get very similar questions around solid lumber, you know, in terms of exterior applications, and how will the timber houses stand up to the climate in India. So design really is everything, I like to say, and with sensible design and good precautions and mitigations in place, we can use almost any material in a clever way. So it's pretty much what the message you're conveying in your presentation. So I had one question about what type of wood is being shown in these mass timber products. I think for most of the structural applications, I'd be correct in saying it's Douglas fir.
Yeah,
but any of our species can be glue-laminated, right?
Of course. So the majority of the examples I showed are Douglas fir, and that's really a preference. Douglas fir has, you know, marginally better structural capability, but it's really the appearance that I'm most drawn to and why I specify it most. Many of those examples, though, particularly the glue-lam arches, are SPF okay, with a stain applied to them. So what you see in Douglas fir is really a beautiful sort of deep orange kind of color, which is, you know, very straight grain, very beautiful wood. The SPF tends to have a little more character to it. Still very beautiful wood, but you know, my preference is to use Douglas fir where I can. But you know, SPF is a very good performing, beautiful wood in itself. It's commonly used.
Yes, I have to agree. You know, and frankly, the Indian audience that we meet all the time, very, very drawn to Douglas fir also, just because of its appearance. So yeah, I don't think there's any disagreement there. Someone actually asked if, you know, because one of the issues, I guess, in India is we don't have any existing manufacturing, you know, in any large way or commercial way at the moment in either glue-lams or CLT. So right now, you know, we're kind of forward thinking. We're talking about these products. They probably have to be imported. There are certainly people interested in looking at manufacturing. I had a question here about whether they can use indigenous trees for engineered applications. I think the answer is yes, but you know, it's an engineered product, so there's a lot more behind it, right?
I think what I would say to that question is that there was a time not so long ago in Canada where, you know, engineered wood products weren't really available. They didn't really exist. You know, we had a lot of sawn timbers and we had a lot of lumber, you know, dimensional lumber. You know, we saw glue laminated beams show up first. And, you know, that was because they ended up being very cost competitive with open web steel joists or other steel fabrications. And so glulam really got going and sort of had a long life with proven record, and it was demand. You know, people like me designing with it because it was, you know, the right thing to do. It was later that the CLT products, the planar, the panel products started showing up relatively recently, and it's through demand. So I would say to my Indian colleagues, if you really want to build with timber, do find indigenous sources where you can, and do put in the work, because I think an industry can be created. We've created one here. We followed the lead of Austria, Germany, Switzerland, you know, parts of Northern Europe. And I'd say that the benefits to building with timber are too important to ignore. So I would say yes, encourage at every opportunity your local industry to develop, because it can happen.
Okay, yeah, good answer. I agree 100%. And that answer kind of covers a few of the questions that came through during the presentation, you know, regarding the scope in the Indian market and where these products can be used, you know, in what geographies. You know, a lot of timber construction takes place, for instance, in hill stations, maybe in the foothills of the Himalayas or in hill stations in the south roads. But no, those kinds of sites do lend themselves to prefabricated products, and whether they're solid wood or engineered. My feeling is that these types of products can be transported, prefabricated, transported, and erected in very sensitive environments, and certainly in difficult, you know, terrain and sloped sites and so on.
It's a huge advantage. You know, the wood is lightweight. You know, the fabrication technologies that we have let smaller pieces be used and connected together. So places like hill stations, you know, more remote locations, we choose timber for those same reasons. In many places that we use it, there's just natural advantages to building with a lighter weight material. When you compare that to wet trades, you know, like concrete, you know, think about building a concrete building. You build typically perfectly good timber walls, fill it up with concrete, then take the timber walls away. Right? You can avoid that altogether if you just build the timber wall right in the first place.
Yeah, good comment. Good comment. I did have a question about, in terms of manufacturing in India, someone's asking, you know, what type of glue is used. I guess that's a relatively simple answer, or no?
Well, yeah, I mean, glues, I think, have evolved a lot over the life of engineered wood products from where they started, which was more urea-based, you know, potentially, you know, more hazardous glues. Now the glues are developed with health effects in mind, with combustibility in mind. So, you know, the environmental standards that the glues have been developed to in Europe and in North America are very demanding. So the glues are incredibly stable. We don't see glue failures really ever in service. You know, the wood's more likely to split or crack due to a failure of some kind rather than the joint of glue. So I'd say that the glue technology is very well understood and very reliable. Okay.
Another question that's been repeated a couple of times is regarding foundations. You know, people are asking in general, you know, is there any, what specifically is needs to be done in terms of the foundations for mass timber buildings? I don't think too much different to concrete buildings, but please give us your thoughts.
No. So I guess, you know, generally we don't advocate for using timber as a foundation material itself. Sometimes we'll use treated wood pilings and under certain soil conditions, but generally we still use concrete foundations, right? We're not trying to eliminate concrete from the possibilities. We want to use concrete where it makes more sense. So we still use concrete foundations. We still connect to concrete foundations using steel. What we do know though is when buildings are lighter, those foundations get to be smaller. So we just have less concrete in the ground. When the superstructure is made out of timber, you know, we can have half the weight or less compared to a purely concrete building.
I just thank you for that answer. I just got another lengthy question there, but again, it's there seems to be there's a big focus on there's so much interest from architects in India, but they have doubts about fire protection, moisture and fungus, and I think we've addressed those. But certainly, these questions are repeated all the time, and they're concerning for people. So, I think, is there any particular treatment that we require on engineered products?
I would say a few things. I've pulled examples from the portfolio that showcase the beauty of wood. There's a lot of cases where wood's just hardworking and it's actually concealed. So an easy way to fireproof timber buildings is to encapsulate them in gypsum board. And we do that all the time. The Brock Commons example that we showed you by Acton Austri Architects was significantly encapsulated with gypsum board. It's a very reliable way of protecting timber. It also relieves the timber of being to the standard of high appearance grade where it's really showcased. So I would say that you need to be sensible in your approach to fire safety. A very practical way is to encapsulate it. You don't get to see it, but it still does the work. It still sequesters the carbon. There's still a great story to doing ordinary hardworking timber buildings that don't necessarily showcase the wood. Now, if you do want to showcase the wood, you need to be more strategic. You need to think about fire sprinklers. You need to think about other ways of protecting the wood. The mildew and mold question is something that I'm preoccupied with, practicing in a rainforest. The west coast of British Columbia, this time of year, we get a lot of rain. So what we need to do is think about the structure in conjunction with the enclosure. So what we're doing now is designing cladding systems that can be modular and prefabricated so that cladding can be installed on the building as the structure goes up. Okay. That's a key. So to avoid having temporary tarps or hoarding to protect the building during construction, the more sensible way is to just put the final cladding on the building right away. So as soon as the active floor is capable of receiving that cladding, enclose it with the final cladding. So that takes pre-planning. It also means doing things a little differently because it means prefabrication generally so that you're spending less time putting it up. But I think that's the key. We want to keep wood dry, absolutely. There's so many examples of wood projects that have lost the benefit of speed or have otherwise created problems because they've been damaged by moisture during construction. Once the building's enclosed, they tend to behave very well. During construction, you need to approach a timber building differently than a concrete or steel building. The consequences are just different.
Okay, thank you, Derek. That's a very detailed and a great answer. I guess it would be remiss of us not to talk about cost comparison. It's always a primary question in India, how much, and we have received some questions today about can we give some kind of comparison of mass timber structures versus reinforced concrete structures.
Yeah, it is a very important question. It's something I'm preoccupied with as well. The bottom line is that mass timber buildings relative to concrete buildings are still a fraction, right? There's a lot of concrete buildings made. We can know to the cent how much a contact foot suspended slabs cost in the present market. Timber buildings are a little different. There's not as widespread of expertise yet. The supply isn't as widespread as concrete. So that means the prediction on price is harder to do. So what we've seen though in our projects is that there's probably a small premium right now for mass timber buildings of this kind. And some people will say as much as 10%. I think that really depends on design and the capability of the people, pricing the work and building the work. So we have seen other cases, though, where the timber option is actually more cost effective. And that's where the building can be erected very quickly. Time is money. And when you can have a system optimized to go up very quick and you shorten the construction window, you save a great deal. So I would say it's an emerging science how to cost these buildings. There's not a consensus. My experience has been that there's a small premium right now, but it's a premium that many owners will accept for the benefits that timber can bring.
Right. Yeah. I couldn't agree more, and I see it as a major positive in India, because while the cost of materials, particularly steel and concrete in India, quite low relative to most other countries. So the material cost is low, but certainly construction times here are very, very slow. I think a prefabricated timber building could be constructed in a 10th or a 20th the time that it currently takes for a concrete building. So there's a huge opportunity cost saving there, and that's where the real savings are in terms of projects. So a very important point.
Peter, we have just 2 minutes more to go. Yeah.
Okay, thanks, Nirmala. So we're still getting more questions as we're continuing. Excuse me, looking at the other screen, Derek. People are asking for examples of more projects, about facades, again about the climate, about coatings. That's a good question. We often get, obviously coatings is a fairly important subject when it comes to timber and external use. Maybe an observation from me. We often see, in Canada, for instance, we might see glue-lam beams protruding, to the outside of the building under the soffit, for instance, as a feature. It's a very attractive feature, and it's in India, people, if they're building with wood, they want to see the wood. And so I'm always at pains to say to people, well, you just have to take into account design and, orientation and plan accordingly, and try not to, put wood directly in the afternoon sun, for instance. Try and protect it in some way, put it under an overhang, shade it, screen it. I imagine you agree with that sentiment.
Yeah, I mean, coatings are an emerging science that we need to have more innovation in. What we want is that wood to look golden and perfect forever. And wood doesn't naturally do that. If we have wood in service, it turns gray over time and it becomes beautiful. And in the Alps, you'll see lots of buildings done this way that are allowed to age. You see the passage of time in the building. We tend not to love that everywhere. So we need coatings. And the problem is that UV degradation of the finish and of the timber itself means that highly pigmented finishes tend to perform better. But highly pigmented finishes kind of conceal the beauty of the wood. So we want clear finishes that can provide that level of performance. And there are some that do better than others. And there's a lot of sort of emerging science on the subject. But if someone, a chemist out there can come up with a truly clear wood finish that is super durable and is resistant to UV and water, the world will beat a path to your door, because it's still not quite there. It does require some maintenance in order to stay golden and beautiful forever. But it's a natural product. That's the price, I guess, when used in service.
Yes, exactly right. Yeah. So I guess we should wrap it up there. Again, thanks so much for a very entertaining presentation. Really appreciate you making the time and sharing your knowledge with our Indian audience. FAI has been quite active now, particularly in the last 2 years, in terms of wood in structural use. So we have some examples, everyone, across India of timber frame houses and tongue and groove solid wood houses and some post and beam houses located in places like Mysore, Chennai, Bangalore, and we have some ongoing projects. So these houses are there. We have a wonderful project in Ahmedabad, the workshop at CEPT University, where we've used glue-lam arches, 11 meters long, and 33 of them in the roof structure. So there's lots of examples right now in India, across India, for you to go and see and visit firsthand and touch and feel. We have other ongoing projects, and we see that engineered wood is kind of the next step. It's the future, and we, as I said at the beginning, we're really seeing a lot of inquiry and interest from architects across India. And the disadvantage we have, of course, there's no manufacturing of those beams. There's one company in Delhi. They're doing a good job on glue-lams, but it needs to sort of grow and become a little more commercial. So that'll come, I think, as you said, Derek. This is a really good taster, and people who are interested in the technology should really start looking closely, and it'll come. It can be done. So again, thanks very much for the presentation. I'm sure everyone enjoyed it. Any questions that we didn't get to, I'm sorry. We've run out of time, but we will get to those questions and provide answers to you via email in the near future. So thanks again, and over to you, Nirmala.
Thank you, Peter and Derek. I think it was indeed a very informative and engaging Q&A discussion we had today. Very, very informative. I think we all will agree that today's session was extremely knowledgeable and allowed us to view some of the wonderful project works of mass timber in Canada through Derek's presentation. Just concluding, mass timber architecture in India is currently in its nascent stage and yet to show any signs of growth in India. Canadian Wood has been involved with many initiatives around building with wood. We truly believe that timber is the world's oldest and only truly renewable structural resource. As stated by Derek, we are not looking at replacing cement or steel. We're just reinforcing the point that whenever you can use a sustainable material like wood, please do so. Around the world, architects are leveraging the strength, stability, and design flexibility of wood products such as CLT, as shown by Derek. It's basically just to push one's notion about wood's perceived boundaries. All we can say is that reimagine the possibilities of building with wood. On behalf of Canadian Wood, I would like to thank Derek once again for taking time out to share some of his wonderful works with us. I know everybody has many questions. We are flooded with questions that remain unanswered, but do allow us time to capture and document these questions from the Q&A panel. We'll come back to you with a mail in a few days' time. If you still like to know more about Canadian Wood, please do not hesitate to reach out to us by visiting the Canadian Wood India website or by contacting any of our business development managers. They will be most happy to assist you. After this webinar, you will receive a survey link from Canadian Wood that will be sent directly to your registered email ID. Request you to please fill the feedback form and share it back with us. Feedback and suggestions are most welcome. We look forward to seeing you again at our next webinar. Thank you. And with this, we end our session for today.
Thank you.
Thanks, Terry. Thanks, everyone.
Thanks. Bye.